Howdy. Good morning, everybody. How are things going today? Got nice sunshine and much better day than yesterday. Hope you're all doing well. Hope your family's well. So I want to jump into explaining the notes, pages 4 through 6 that you copied down yesterday. Before I get into it, I just want to let you know, in case I forget later on, I hear a lot of teachers are doing what's called a Flipgrid platform for you to share short video clips or whatever. And so I think I made mention earlier about having you take part in Decision Day, the day where you get to share with everybody what your plans are for next year, whether it be college, whether it be a 2-year trade school, whether it be service in the military, whether it be taking a gap year, just working to save money and to go to school in the future. So go to that. It's at the very top of under distance learning. The very top link is to says Decision Day 2020, and opportunity for you to go there and take a quick video. Tell us what you're doing, regardless of what it is. It's cool, and so I'd like to hear that. Okay, so let's get into the parallel circuits. In the series circuit, remember the number one characteristic of a series circuit was that it had only one path for the current to flow, and the current was the same everywhere. Well, in a parallel circuit, there's more than one path for the current to flow, and therefore the voltage is the same in all branches. So hopefully you have your notes out in front, and I can share these with you. So I now would draw this picture over here on page 5, or the second page for today, which is the black lines that you see here. This blue line, just kind of forget about it in your mind for a minute. That comes up later in the lecture. So I have two 6-ohm resistors in parallel. Okay, so they're side by side. The current comes here and has a choice. It can go to that branch or it can go to that branch. Okay, but in either case, the voltage, 12 volts, is the same as our 12-volt battery. That's a characteristic of a parallel circuit. Okay, probably a good time to talk about some examples of a parallel circuit. Well, a really simple one is the headlights in your car. The headlights in your car are wired in parallel for a very logical and safe reason. If one of your headlights were to hit a rock, or a rock were to hit your headlight, that bulb is going to shatter. And if they were hooked up in series, both headlights would go out because they're connected along the same wire, only one path. Whereas in parallel, your left headlight could go out and your right headlight is on a separate wire, meaning this could be your left headlight, this could be your right headlight. The current's still going to go through this one and you still have light, so you can still drive safely. Your home is wired in parallel. The school is wired in parallel. Commercial, residential, everything is wired in parallel. So you have your bathroom circuit goes out because you have too many things on. We'll talk about that later as well. That doesn't mean your whole house goes out. Just that portion of the house, just that branch of your circuit, of the multiple circuits that you have in your home. Okay? Okay, number 2, total resistance. If you remember in series circuit, the total resistance is just like the denominators here. RT equals R1 plus R2 plus R3, whatever. In a parallel circuit, it's called the reciprocal rule. And we can get into it more later, but the rule is 1 over RT equals 1 over R1 plus 1 over R2 plus however many you want. So in our example over here, up in blue, I have 1 over RT equals 1 over 6. I have a 6-ohm resistor for number 1. I have a 6-ohm resistor for number 2. 1/6 plus 1/6 is 2/6, reduces to 1/3. Now remember, 1 over RT is 1 over 3, so RT is 3 over 1, or 3. Okay, so you make sure you have to flip it. So that's the total resistance in a parallel circuit. There's a second rule that works also, equation, and that's called the product over the sum rule. You could take R1 times R2 over R1 plus R2, and that would look like, I think I have that, right here. 6 times 6 is 36, over 6 plus 6 is 12, which equals 3. And the third method for finding total resistance is very restrictive because it only works for pairs. This one only works in pairs too. You can't do R1 times R2 times R3, but this only works for groups of 2. And if they're identical pairs, then we could just simply cut them in half. So 2 6s make a 3. So this one works for everything. It's a catch-all equation for total resistance. A little more restrictive, and it only works in pairs, but they don't have to be identical. And this one, they do have to be pairs, and they have to be identical. Okay, current. Total current, same as before. Total voltage, total resistance, Ohm's law, solving for current. The sum of all of your currents in each of the paths need to add up to equal your total. So if we go over here, my total current is going to be 12 volts. That's the total voltage. We just found total resistance is 3. 12 divided by 3 is 4. Okay? Now my branch current in branch number 1 is the voltage at 1 divided by the resistance at 1. Well, we know the voltage is 12 because it's a parallel circuit. It gets the same. So 12 divided by my 6 ohm resistor up here. 12 divided by 6 is 2. Down here, same. 12 divided by 6 is 2. And 2 plus 2 equals 4, which is my total. So that's a good way to check and see if I've done my math correctly. All right. Lastly, it says RT goes down as you add more branches. Total resistance lowers as you add more branches. Let me share with you what that means. So here's where this blue resistor comes in. Let's assume that I have 3 6 ohm branches. There's a 6 ohm resistor, a 6 ohm resistor, and a 6 ohm resistor. If I were to go ahead and do my total resistance now, I would get 1 over 6 plus 1 over 6 plus 1 over 6, which adds to 3 over 6. I flip it to get RT. 6 over 3 is 2. Well, before I had 3 ohms. Now when I add another resistor, I have 2 ohms. So in fact, my resistance went down as I added more branches. Now, that may seem like, okay, I get it, but let me give you a practical example of that. And this should hit home very well with you, I would think. Let's say you wake up this morning, and or in the winter morning, maybe more appropriate. You kind of groggily walk into the bathroom, you turn on your lights. You turn on the exhaust fan because you're going to take a shower. You plug in your hair straightener if you have hair. You turn on the radio. You have a heat lamp in the ceiling. You have in-floor heating in your tile. You turn on all of these devices. What is the natural outcome if you turn on too many things in your bathroom circuit? What happens? What we used to say is we'd blow a fuse. Now we say we just trip a circuit breaker. So you have to go down into the basement or out in the garage, wherever your circuit breaker box is, and turn it from the off position to the on position. In the olden days, we literally had to take the screw out because it was blown. And that means that this whole circuit would shut down. This is your lights, this is your ceiling fan, this is your heat lamp, another one would be your hair straightener, etc., etc. The more branches you put in, the lower your resistance. So let's look at this number right here. If this resistance right here goes down, okay, then this current goes up. That means the current's going to get higher than before. And if your current gets too high to exceed the limit of that circuit breaker, or in the olden days of that fuse, it blows, or it trips, or it flips, whatever phrase you want to use. But in the old days, fuse would literally blow and you'd have to go buy a new one. They're not replaceable. Whereas circuit breakers are replaceable. You just flip the switch from the off position to the on. But it's designed to have a maximum amount of current. So let's say this circuit had a maximum amount of current of 5 amps. Okay, so here we're safe. 4 amps, we're okay. But then we put another branch in, we get 2 ohms of resistance. 12 divided by 2 is now 6 amps. That's higher than our 5 amp limit, and pop, the circuit breaker blows. or the fuse blows. Okay? So that's what happens when you add more branches, when you turn more things on in your home. The resistance goes down, and when resistance goes down, the current goes up. When the current goes up, it's usually unsafe because current going through a wire gets the wire hot, and that could cause an electrical fire in the wall behind your outlet, and that's why the circuit breaker or fuse is placed there to prevent that from happening. So it does its job when it breaks or blows. Okay, so those are the four characteristics, if you will, of a parallel circuit. And I'm going to come back with one more video, and I'm going to explain that sample test question that's on page 6 of your notes. Okay?